Why can you never trust atoms?
Why?
They make up everything.
Oh, Misty, that was great. Wait, I got one. Do you want to hear it? Okay. Why did the robot cross the road?
Why?
Because he was programmed to do it. Come on, that was great. Oh, what a tough audience. Hiyo, friends. It's me, Gore, and welcome to Adventures in Summer Reading. And no, Stick did not turn into a robot. This is Misty, the library robot. Can you say hi, Misty?
Hi, Gore.
That's great. Haha, affirmative. Misty is joining me today for our special guest, Kentucky Science Center. I am so excited. I wonder about science all the time. Like, where do boogers come from? And why do pine cones taste so delicious? How do robots work? How do you work, Misty? Science! Hey, Misty, I bet you're wondering why I'm wearing these safety goggles, aren't you? Because Kentucky Science Center is in the makerspace today, and they're getting ready to blow up volcanoes or make toothpaste. Or did they say they were going to make volcano rockets or rocket toothpaste that explodes? I can't remember. Oh, hey, Missy, maybe you could give me a countdown when the explosion will happen, and then I'll know to put on my goggles and take cover, okay?
3, 2, 1.
It's happening! Take cover! Misty! Oh, did you trick me again? Oh, good thing the explosion's not happening.
3, 2, 1.
This is it! It's live, people! Get your goggles! Misty, you are such a jokester! You got me again. Well, let's get to the makerspace and see what the Kentucky Science is up to. Misty, you're going to stand in front of me this time. I don't want to get anything on me.
Hi, I'm Scientist Veronica with the Kentucky Science Center.
And I'm Scientist Andrew, also with the Kentucky Science Center. And we have a variety of activities that you can do at home as part of the summer reading program.
Yes, so we're going to be focusing today on reactions. So we have a lot of materials you might have in your home, and that way we're going to do some explosive results.
So the first reaction we're going to explore is the baking soda vinegar. It's a classic reaction, acid-base reaction. And we are going to build some volcanoes, some like that old-fashioned science fair volcano model that you can scale up for different ages and try at home.
We're going to be focusing on first our volcano, which is our simplest. We do it for our pre-K camp. All you need for this experiment is some Play-Doh, a paper plate, a couple markers. We recommend blue and green, but other markers will do. A Dixie cup, and then of course our baking soda and vinegar. So the first thing I'm going to do is take my plate here, and I'm going to design the land where I'm going to form my volcano.
So, we sometimes recommend with the children when we're doing this in a camp that you can draw water on the outside, draw your blue water on the outside, and draw the green land closer in the middle where you're going to place your volcano. This is because a lot of active volcanoes occur near water where the plates of the earth meet or separate. Commonly, you'll find a lot of volcanoes in that Pacific Ring of Fire around the Pacific Ocean. So we are going to make a sort of model of that. While she is working on the pre-K version and creating her base, I'm going to show you how you can do a sort of a scale up slightly of a little bit more mature version of a volcano by taking a paper drinking cone like this, cutting the top of it off. Whoop, there we go. And go into your antique chest at home and find a film canister and place the film canister under the cone like this so you can create your nice volcano base. We do this for second and third grade camps. This is part of our Kaboom camp to build a volcano. This is sort of a 1 to 2 day activity, and if you're interested in more information on our camps, visit us at kyscience.org. So while she's finishing up the base to that volcano.
Yes, so what I'm doing, I covered my ocean, and now I have my land. So now we get our Play-Doh, and we get our Play-Doh out, and our Dixie cup, which is going to act as the volcano where the lava erupts. So I'm going to start to flatten my volcano landform out. So I do recommend, this can be a little messy, so if you want to put newspaper down or get some tablecloths, and then you kind of just form it around your cup.
There are three major types of volcanoes. Really large domed shield volcanoes like you find in Hawaii, smaller cinder cone volcanoes, and then the volcanoes we're making are representative of stratovolcanoes or composite volcanoes. These are the biggest, sort of most picturesque volcanoes. Think of things like the mountains out west or Mount Fuji or something like that. This is the kind of volcano that has steep sides and a very large crater at the top. If that crater is of a certain size, we call those calderas. So that's looking,
I think that looks pretty
looking
good.
pretty good. Yeah, so
All
you've
right.
got your volcano going over there. Over here on my side, this is where you would, and after you've completed this step, you would then mix plaster of Paris and some water and form a nice paste and cement this down to a paper plate or the surface that you want to erupt on. That's going to take a little bit too long to show you right now, but I do have some examples that we made in camp. This version that I made, unfortunately my plaster was a little thin, so it's less volcano and more wizard's hat. But somebody else from the camp helped out and made a really nice version here that has a little bit more texture. And then of course, once that plaster dries, you can paint it. You've got your brown for the sides of the mountain and just sort of a little bit of lava that's already erupting, painting that in orange. Lava is formed when plates of the earth come together or separate, and that hot magma is pushed up from the mantle into the crust. When that magma reaches the surface, we call that lava. All the different types of eruptions and volcano formations are largely determined by the chemistry of the minerals inside the magma. So whether that is a quick, violent eruption like you would see on a composite stratovolcano like this, or a slow oozing eruption like you might find in Hawaii, all depends on the mineral composition of the magma inside the earth.
Well, I think all our volcanoes are looking great, but now we get to the fun part.
Yes.
The chemistry, the
Yes, let's do
lava
it.
explosion. All right, so what we're going to be using here, we're going to be using baking soda. Baking soda is a base, and we're going to make our reaction by adding an acid to it. So I would say, well, just a couple of teaspoons should do it. And then next we have to add our acid, which today we're going to be using vinegar. Vinegar has acetic acid and water in it. That's very important. But because we're doing lava, I do recommend that you add some red food coloring to it. A few drops. And then once we pour the vinegar into our baking soda, the base is going to react and then release a gas called carbon dioxide. That's going to be the fizzy fun sound that we're going to get.
Okay.
So, all right.
I think we're ready.
Are we ready?
Yeah, let me ask. We've got white vinegar and baking soda like you would find at your home. What would happen if you mixed it up, maybe tried like apple cider vinegar?
That's a great point. That's actually something we encourage you guys to do at home. We encourage you to mess with different variables of what types of vinegars you have, or if you can put different ratios of baking soda into your volcano.
So it sounds like you don't know.
Do you?
No, you're right.
Okay,
Mix up those variables, try different things at home, and play around with this. That's part of the fun. You're exactly right.
So are we ready for our lava?
I think we're ready for
All
the
right.
reaction.
So in 3, 2, 1.
Look at that.
Oh, look at that.
Fantastic.
Oh, that's awesome. Add a little bit more.
Try a little bit more
Woo!
on mine,
So
too.
again, I do want to point out that this can get messy. So our paper plate is doing a good job keeping this together, but you can also use baking trays, pie trays, pie tins. Any of those things will work.
Fantastic. Well, we've got our volcanoes. We've erupted our volcanoes. Do you have anything else we can use while we have these materials out on the table?
Well, I see that you used a film canister for your volcano.
I sure did.
So where did you get this film canister from?
From the antique chest.
Yes, so obviously these were once very popular, but you can order them on Amazon. You can also test this out at home with other materials. All you really need is a tube with a good seal. So we're going to take our film canister, we're going to do another acid-base reaction. So I'm going to move my volcano right here. And again, this is another one that's going to be an explosion. We're going to make Alka-Seltzer rockets. So I do highly recommend that you get a nice area outside. Would be wonderful for this. So we're going to take Alka-Seltzer, we have water, and our film canister.
Okay.
So Alka-Seltzer is a neat product. It has sodium bicarbonate and citric acid. So it is a solid right now, but when we add the water to it, it's going to have that same acid-base reaction. So it's actually going to create carbon dioxide. And this time we're going to capture those bubbles into our film canister.
Fantastic.
So,
How much should we use?
I'm going to recommend about a tablet.
Okay.
Again, this is something you can experiment at home. I also like to crumble mine up because I think there's a better chance for more gas exchange, more carbon dioxide.
Increase the surface area.
Yes. Okay. And since we are messing with stuff, with reactions that have some type of explosive element, it is very important to make sure you have eye protection. All right, so I got my cap, got a surface.
I'm going to put a little bit of water in here.
All right, are you ready?
Yes,
All right, so in 3, 2, 1, little water. Then try to get a good seal. Now sometimes.
Woo! There you go.
All right. That was great.
Yours did a lot better than mine.
Well, you can actually see the bubble still reacting, so we were able to capture that gas. So again, it's the base of the sodium bicarbonate, the citric acid reacts with the water to create carbon dioxide.
Fantastic. How about we get to our finale?
Oh, that sounds great. So one of the favorite things we like to do at the Science Center is we like to do our elephant toothpaste. It's a wonderful explosion that we do in our atrium. Andrew, so you've done lots of our atrium shows. Do you mind showing me how to do this?
Certainly. So because we are going to be using 30% hydrogen peroxide, which is about 10 times stronger than you can get at the drugstore, we are going to take just a moment and put on some safety gear, including gloves, our wonderful green Do Science lab coats at the Science Center, and some heavy-duty goggles. So give us just a second, and we will prep that for you guys and show you these elephant toothpaste reactions.
All right.
We're all set there. Put these on right here. Now, we are going to step in front of the table and bring out some plinths and show you these flasks that have, like I said, 30% hydrogen peroxide in them. Hydrogen peroxide is H2O2, and that is a very weak bond. That wants to convert to H2O and O2, so that hydrogen peroxide is slowly turning into water and oxygen as we speak. What we are going to do is we are going to add a catalyst and speed up that reaction so it happens very, very quickly and create what we call elephant toothpaste. So it's going to create a lot of gas. We want to trap that gas with some soap. So you can see we have added some blue food coloring and some blue Dawn dish soap to these flasks. So we're going to capture that so it hopefully shoots up in a big column, which is why we call this elephant toothpaste. For a catalyst, we are going to be using potassium iodide. And potassium iodide is not reacting to the hydrogen peroxide. It is speeding up an existing reaction. So it's just speeding up what is already happening, although we can't see it right now. So
we do have actually an element. You can do this at home. All you need is 3% hydrogen peroxide. Again, scientist Andrew said that what we're using is 30%, so that's why we have to make sure we have all of our protection. But you can find 3% at a lot of different stores. And then also you're going to be using yeast. So if you can get a water bottle, some hot water to activate the yeast, and then mix that with the hydrogen peroxide and some Dawn dish soap, you can have a reaction similar. So the activated yeast is going to act as that catalyst instead of our potassium iodide.
Okay. Are you ready for our finale?
I think so. All right.
All right, let's do it on 5 this time. Are you ready?
All right, ready.
So, 5, 4, 3, 2, 1, pour. Whoa!
Whoa!
Fantastic.
Awesome.
Yes.
All right, you can actually see the steam since it's an exothermic reaction. So that was great.
So thank you. On behalf of the Kentucky Science Center, I'm Scientist Andrew.
I'm Scientist Veronica.
And we'll see you next time.
Wow! Misty! Did you see all that? Volcanoes, rockets, explosions! Boom! Oh, you're always so excited over there, Misty. Calm down. Well, anyway, let's keep this science going. Miss Amy will be reading a story called Solving a Puzzle Under the Sea. Let's listen, Misty.
Hi friends, my name is Miss Amy. I work at the Louisville Free Public Library, and today I thought we could share a biography, a children's biography about a super important scientist from the 1940s that helped us discover what the bottom of the ocean looks like. So I thought we could read this book together. It's called Solving the Puzzle Under the Sea. Marie Tharp Maps the Ocean Floor. The author is Robert Burley, and the publisher is Simon & Schuster. Maps. I love them. I love the flow of colors and lines. I love the way I can trace a path with my finger across mountains or valleys until my finger has traveled thousands of miles from here to there on just one page. I sometimes feel a map is talking to me. Marie, it says, have an adventure, explore, discover something new. And once I did. I'm Marie Tharp, and my love of maps began way back in the 1930s when I was a girl. My father's job was to make maps that helped farmers understand different types of soil and what they could be used for. I liked to watch as Dad drew his maps. Sometimes I held his pads and pencils as he worked. Dad traveled from state to state making his maps from Michigan to Iowa, Alabama, and beyond, and the whole family moved along with him. I attended 17 schools by the time I graduated high school. Try topping that. Sometimes in class, I'd gaze at a large map that hung on the wall. There was France, there was South Africa, there was China, and always the vast oceans. I had never seen a real ocean. What would it be like to look out at nothing but dark blue as far as the eye could see? When I was in college, a teacher pointed out that though the oceans covered more than half the Earth's surface, scientists knew very little about the bottom of the seas. And what did the seafloor really look like? No one seemed to know for sure. At last, I was a young scientist, graduated from college and eager to work. But was science ready for me? In those days, it wasn't easy being both a woman and a scientist. Once I applied for a scientific job, they told me, we don't need any more file clerks. Because I was a woman, they assumed the only thing I was capable of was taking care of their files. Even at the Ocean Studies Lab at Columbia University in New York, my first boss, Doc Ewing, told me a woman couldn't go out on the research ships. Having a woman on a ship is bad luck, he said. I was amazed. It was 1948. Wasn't science supposed to be free of silly superstitions? But I bit my tongue. This wasn't going to stop me. I was determined. I took on every little task I could, helping there, helping here, assisting there. Yes, I was bored sometimes, but I kept on. I was looking for something that really excited me, something that might lead to a new idea in the world of science. At the lab, I worked hard and made lots of new friends. One of those friends was Bruce Hazen, a colleague who worked with me on several projects. Both of us were interested in breaking new ground. How deep were the oceans? Were there mountains beneath the sea? Or was the bottom mostly flat? One day we had an exciting idea. Could the seafloor be mapped? I thought so, and I wanted to give it a try. People attempted to measure the depths of the oceans. Sailors once lowered weighted ropes to make measurements. Most recently, scientists had begun using machines that sent sound waves from a ship to the seafloor and back again. Using the time it took for the echoes to go and come back, it was possible to figure out the depth at various points. These measurements are called soundings, and as time passed, more soundings were made, including some by my friend Bruce, and these soundings gave me my starting point. You have to think big, I told myself. I hauled a large table into my workroom and covered it with a huge sheet of paper. To me, it was a blank canvas filled with possibilities. I couldn't wait to get started. I began by drawing coastlines, the Americas, Africa. Between these coasts lay my target, the wide Atlantic Ocean. Next, I collected all the soundings available and placed their numbers carefully where they belonged on the map. Each sounding told the ocean's depth at some point. If a sounding number was 16,000 feet, it meant that the ocean was 16,000 feet deep. And if a nearby point was only 8,000 feet, the sudden difference between those two numbers meant that there was probably a mountain-like peak rising upward. Yes, there are mountains beneath the ocean, just like on land. It was like piecing together an immense jigsaw puzzle. I felt like a detective solving a great mystery. I was a scientist at last. I was kind of an artist too. I used colors to shadow similar depths, shades of brown, blue, and green. Did all of this take time? Yes. Even so, making a scientific discovery is worth it. I couldn't see it with my eyes, but a portrait of the ocean floor was coming into view. I noticed something else, something new and important. The depth numbers on my map suggested a deeper valley beneath the seafloor that divided the mid-Atlantic into two parts. At that time, most scientists believed the Earth's surface never moved. The Earth, of course, moved around the sun, but the Earth's surface, so these scientists assumed, was unmoving. Other scientists thought differently. They had an idea or hypothesis that the Earth's entire surface was divided into plates. They thought these plates were being forced apart by earthquakes and volcanoes beneath the sea. And because the continents rested on these plates, they moved. The new theory called plate tectonics or continental drift. Was this theory true? I believed it was. My map showing the deep crack or rift running between the mountain peaks of the Mid-Atlantic Ridge was telling me so. Was I proud of myself? You bet. I had a fascinating job that led me to map a once unknown part of the Earth and discover things as I went along. That's about as big as it gets. And my map helped prove that the Earth's surface is moving too. But don't worry, you won't lose your balance. We're only moving about an inch or two every year. Thanks for learning about Marie Tharp with me. Until I can see you again, keep reading.
Oh, thank you, Miss Amy. Wasn't that a great story? Wow, Marie Tharp was amazing. It takes being an artist and a detective to be a scientist. Miss Maria Thorpe said, you have to think big, and that's what we've done today. From volcanoes to elephant toothpaste to robots. Right, Misty? Oh, also, I want to thank the Louisville Free Public Library. Misty, tell our friends how to sign up for the summer program.
Just go to the library's website at lfpl.org.
Yeah, thanks, Misty. And don't forget, friends, if you read, you get prizes. Until our next adventure. Hey, Misty, let's get out of here. You want to go grab a couple megabytes for lunch?